All right, let's take a look at graphing motion. And so we looked at motion diagrams as a way to visually represent, an object's motion. But typically, motion diagrams are only used, at a very basic level. Most of the time, we're going to be analyzing graphs. So there are going to be three types of graphs within kinematics that you're going to have to be comfortable with. Your position versus time, your velocity versus time, and your acceleration versus time. Now, our position versus time graph shows the object's position over a certain time interval. So if, for instance, we were to look at this example of the car in example 2.1, the car starts at position positive 10. It moves towards the origin, passes through the origin, moves to negative 20, and then for about 10 seconds, what happens? Well, it sits here at negative 20 stationary. Then what does it do? Well, it starts to move back towards origin and finally reaches origin at 80 seconds. Right? So looking at your x-axis determines, where is the car at each particular point in time. Now, you always want to examine what three different things on your graph mean. So we got position in meters, time in seconds. And let's say we've got a graph that looks like this. Well, we've already looked at what the axes mean, right, with that example. Right? If your line is up here in the positive, it means that it's in the positive position. If it's here at 0, it would be in the origin, right? So this one originates at origin and moves towards the right. And if it's down here, it's in the negative position. Now, besides looking at the axes and thinking about what they're telling you about this graph, you also want to look at the slope, right? Because a lot of the times the slope will represent something important to us. And the easiest way to do that is to look at the units. Well, if we look at finding the slope, which would be rise over run, well, what's our rise measured in? Meters, right? What's our run measured in? Seconds. So whatever the slope is representing is measured in meters per second. Well, what do we know is measured in meters per second? Well, velocity. Right? Alternatively, you could look at it just from an equation point of view. What's our rise? A change in position. What's our run? A change in time. Oh, what's a change in position over a change in time? Well, that's velocity. Right? So you always want to look to see if the slope represents anything at all. Now, the other types of graphs you might see, again, I'll put that position time graph back up here, is your velocity time graph. Now, what if we wanted to make a velocity time graph here that corresponds to this position time graph we just did? Well, if the slope here represents velocity, what can we say about the slope? Well, it's a straight line, right? It's linear, so we know the slope is constant. What else can we say about the slope? Well, it's positive, right? So we've got a positive constant slope on this position time graph, which means the velocity here is positive and constant. So if we wanted to graph the velocity versus time graph of this object, it would have a positive constant velocity. Right, again, on your velocity time graph, if your velocity is above 0, it's positive. If it's below 0, it's negative. If it's at 0, it's stationary. And by positive or negative velocity, we're just talking about the direction of the velocity. Which way is it heading? Towards the negative or towards the positive? So we've looked at what the axes mean here. Let's look at what the slope means. Well, the slope here is 0, right? But let's look at it in terms of units. So again, looking at rise over run. What's our rise measured in? Meters per second. Our run is in seconds. So meters per second, which is the same thing as meters per second squared. Well, what do we know is measured in meters per second squared? That's acceleration, right? Alternatively, again, you could look at it in terms of your formula, right? The slope would be a change in velocity over a change in time, which is acceleration. Now the slope here is 0, right? Meaning there is no acceleration. And why does that make sense? Well, what's true about your velocity? It's constant. So the slope of your position versus time graph gives you velocity. The slope of your velocity time graph gives you acceleration. Now, I said there were going to be 3 things that you want to analyze on each graph, right? So axes, slope. The third thing you always want to check is area under the curve, right? Because the area under the curve will often represent something in a lot of these graphs that we do in this class. So if we wanted to find the area underneath this curve, right, it would be base times height, right? Well, let's look at it in terms of units. What's the base measured in? Well, seconds. What's the height measured in? Meters per second. What happens to our seconds here? They cancel out, right? Meaning that whatever is represented by the area underneath this graph is measured in meters. Well, what do we know is measured in meters? Displacement, right? So you can find the displacement of this object by finding the area underneath this curve here. And so on the Google Classroom, I've uploaded this document. I think it's called Graphs Cheat Sheet. But it basically gives you all of the different sections of graphs you might see in this class, right? So if you see a portion of a graph that is linear, right, what you're seeing is that it's traveling with a positive constant velocity, meaning acceleration is 0, right? So these 3 graphs here, this position time, this velocity versus time, and this acceleration versus time graph, they all show the exact same thing just from different perspectives, right? So this shows positive constant velocity, this shows positive constant velocity, and this shows no acceleration. Now this graph here shows negative constant velocity. Well, how do we know it shows negative constant velocity? Well, again, the slope represents velocity. The slope is constant, right? It's linear, and the slope is negative. Well, how do we portray that in a velocity versus time graph? Well, you've got a constant velocity in the negative. Now your velocity is constant, which means what is true about your acceleration? Well, acceleration is 0. All right, now what if we've got acceleration involved? Well, if you have acceleration, you're going to have exponential growth or decline in your position versus time graphs, right? Meaning that you're going to have a slope on your velocity time graphs indicating that the velocity is changing, right? It's either increasing or decreasing, right? And so your acceleration, which will be constant for us because otherwise you need calculus, will just always be a straight line, either positive or negative. Right, so I want you on your own time to take a good look at these. See if you can reason them out. If not, that's something we will cover in depth on one of our live engagements. But I think this document is really clear about all the different graphs. So definitely take a look at that. So let's take a look at a couple of examples real quick together. All right, which position versus time graph best describes the motion diagram at left? Well, here you've got constant velocity, right? And what do we have here? Well, we have constant velocity here also, but it's a bigger constant velocity, right? So the object is traveling with some amount of constant velocity, then it travels with a greater amount of constant velocity. So if we want to find the position versus time graph that best suits this motion diagram, we need to find 2 sections of constant velocity. All right, so again, if you look at your motion graphs, constant velocity will be linear. Now we can throw this out because what does this graph tell us? Well, it tells us that the object is stationary up until this point of time, and then it teleports to a new location and is stationary there. So we can throw that guy out. Now what about this guy? Okay, it shows two sections of constant velocity, but why is this one wrong? Well, notice that this is a greater constant velocity than this, which means that the slope of your position time graph for this section needs to be steeper than the slope of this section. Right? This shows an object traveling at a constant velocity, then traveling at a lower constant velocity. So we can throw him out. This one just shows a constant velocity all throughout. We can throw that out. This is the only one that shows an object traveling at a lower constant velocity, then switching to a greater constant velocity. Right? So again, the steepness of your slope is going to tell you the magnitude of your velocity. Right? A steeper slope means a greater velocity. All right, let's take a look at 2.2. We got four objects. They move with the velocity versus time graph shown below. Which object has the largest displacement between time equals 0 and time equals 2? Well, how are we going to find the displacement given your velocity versus time graphs? So remember, you always want to look at three things. The axes, what do they tell you? The slope, what does it tell you? And the area under the curve, what does it tell you? So in this case, the slope gives us acceleration. That's not helpful. But the area under the curve, right, if you look at your units, meters per second times seconds, your seconds cancel. The area under the curve is measured in meters, which means that that's going to give you the displacement. So by finding the area under the curve, you're going to find your displacement. So let me get a calculator here. For option A, you have 2 times 1, you've got a displacement of 2. I don't know why I grabbed a calculator. For B, you've got 2 times 2, you've got an area of 4 under here, so 4 meters were traveled. Here, 2 times 1, you've got an area of 2, so 2 meters were traveled. And here you got 1.5 times 1.5, which I can't do mental math, which gives you 2.25, so 2.25 meters were traveled. So this one, having the greatest area, 4 meters, traveled the greatest displacement. And that kind of makes sense, right? If you're thinking about it, yeah, it was traveling at a fairly large speed compared to the others for a much greater time compared to the others. All right, which velocity versus time graph goes with the position versus time graph on the left? So again, before even looking at your options, I would just trace through here and think about what's happening. So the object starts in the negative, and it moves towards origin, past origin, slows down and stops. Now notice, what can we say about the slope here? Well, it's constant in this section, right? And what else is true about the slope there? It's also positive. So what we need to be looking for in our options is something that has a positive constant slope initially. Well, what's the only graph here that has a positive constant slope? Well, option C, right? So let's continue and think about, does option C actually fit? Well, what happens at the end? Your position starts to taper off and the guy becomes stationary. Well, what happens? Velocity starts to taper off and he's stationary. Right? So option C is the only one that would fit. So again, it's looking at whether this is positive or negative constant velocity. Right? That would determine whether you were choosing between C and D. So always look at the slope and determine if it's a positive constant or a negative constant. All right, now if you're looking for whether your acceleration is positive or negative given a velocity time graph, again, the easiest thing to do is just look at your slope, right? So here you've got a positive slope, which means that you have positive acceleration. Here you've got a positive slope. You've got positive acceleration. Negative slope, negative acceleration, negative slope, negative acceleration. Now the problem comes in when someone looks at this graph and they go, but the object's slowing down. How can the acceleration be positive? Well, it just means that the object has a leftward velocity, and if an object has a leftward velocity but a positive acceleration, it's going to slow down. Right? So if velocity and acceleration point the same direction, the object speeds up. If acceleration points opposite your velocity, it slows down. Right, so this would show an object that is traveling in the positive and speeding up because it has a positive acceleration. Positive velocity, positive acceleration, speeding up. This one has an object with a negative velocity but positive acceleration, it's slowing down. This one has a positive velocity but a negative acceleration, right, because the slope is negative, so it's slowing down. This one has a negative velocity and a negative acceleration, therefore it's speeding up in the negative, right? If you were to put numbers on this axis here, it'd be -1, -2, -3, -4, -5, right? It's speeding up in the negative direction. All right, so let's say we've got ourselves an elevator, it's moving downwards and slowing down as it approaches the ground floor. Determine which of the following graphs best represents the motion of the elevator. All right, so the elevator is moving downwards. Now we've talked about positive and negative velocity in terms of left and right. Well, if you're doing up and down, guess what direction is positive? Up is positive, down is negative. So it's moving downwards, so we know that it has a negative velocity. And we also know that it's slowing down. All right, so you want to look at your four options. We know that its initial velocity needs to be negative because it is moving downwards. So we can automatically throw out A and C because their initial velocities are in the positive quadrant. So it's down between B and D. Well, we also know that it's slowing down as it approaches the ground floor. Well, D shows the object starting with a small negative velocity and increasing that negative velocity as time goes on. So this object is speeding up as it goes downwards. Now B, on the other hand, shows us something that starts with a large negative velocity and slows down towards 0. Right, so that would be the elevator in question here. Right, as it approaches the ground floor, its negative velocity decreases towards 0. Now again, I would take a look in depth at this document. It's real handy. Yeah, your graphs may be a lot more complex, like say something that looks like, say a position versus time graph that looks like this. Right? But if you use that cheat sheet that I uploaded, you just take section by section and look at the motion handout. Right? So break it into 3 different sections. You got 1 here, you got 2 here, you got 3 here. Well, let's only look at part 1. Well, if we look at our cheat sheet, what does 1 show us? Well, 1 shows us positive constant velocity. If we look at section 2, what does section 2 tell us? Well, no velocity, right? It's stationary. What does section 3 tell us? We've got this exponential curve right here. Well, it tells us that you have changing velocity, right? And your acceleration is positive. Right? So you've got an object speeding up. Right? So using that cheat sheet, you can break more complex graphs into small sections and determine what's happening over each period of time. So I'm going to upload a couple of problem sets. One is going to be called basic graphing scenarios. That will be the one I would start with first. And that one allows you to kind of just qualitatively sketch graphs. Now I'll put a answer key up as soon as I have a chance. And then the second one will be more numerical based. So I want you guys to give that a try after looking at this and looking at the notes and our motion graphs or motion graph cheat sheets. But again, I would keep this guy handy whenever you're working with graphs because it's very, very helpful. So make sure you really look at it, think about what it means. If you have any questions about this document, please let me know. We'll talk about it. But yeah, I will see you all soon.